The second film about the deflection bridges and converting from change in resistance to change in voltage. So with the last film we looked at this, how it changed resistance to a change in voltage. But it can of course also be used for capacitors and inductors, where you have a change in impedance or capacitive or inductive reactance into a change in the voltage. Tool is to use the Whetstone bridge, and the voltage is measured between two voltage dividers. So this is a voltage divider and this is a second voltage divider, and you measure the voltage between the two here. At least one of the impedances is unknown. We will look at later how we can have more than one unknown in such a bridge. Now, when we have such a bridge like this, there are two ways to use it, and it's as a balanced bridge and an unbalanced bridge. And here is the equation that we ended up with in the last film. Note that in this film here, that the polarity between the two has changed because we now measure plus here and minus there. If I measure with the voltmeter with a plus here and minus there, we end up with different signs for these two. So let's study how balanced and unbalanced bridges work. Let's draw the basic circuit again. I have now in red Vs, supply voltage, the 4 resistors that can indeed be inductors or capacitors as well, point A and point B, and finally a ground in the corner. That's the reference. Name them R1, R2, R3 and R4. Now for a balanced bridge, what we do is that we have one sensor and then we have one variable resistor, a potentiometer, like that. Now the variable potentiometer here makes it possible for us to adjust the voltage here or adjust the resistance here to match the one on this side. So if these two R1 and R3 are equal, we can now we can now balance the bridge so that these two are equal. Let's put down the equations, and let's put it down like we did in the last film, with plus reference here at terminal A and minus at terminal B. So VAB equals supply voltage multiplied by R2, R1 plus R2 minus R4, R3 plus R4. Now, if the bridge is balanced, what we do is that we have our sensor here and our variable resistor there. I adjust the resistor until I measure 0 volts across the terminals A and B. If I measure 0 volts, I can really fine tune it because I can adjust the voltmeter so it measures millivolts and finally microvolts until it's definitely 0 volts across the terminals. If I have 0 volts across the terminals A, B, it means that this part of the equation is 0. Or VAB equals 0 means, as long as I still have a supply voltage, that R2 over R1 plus R2 equals R4, R3 plus R4. Now let's do on these two fractions here. On the first one, I divide every element with R2, and on the second one, I divide every element by R4 and see what I end up with. If I divide every element on the first part with R2, I get R2 over R2, 1. R1 over R2 plus R2 over R2, 1. And the same here. R4 over R4 is 1. R3 over R4 plus R4 over R4, 1. Since this equal sign is here, all the ones are equal, then this one must equal this one. So now I get that R1 over R2 must equal R3 over R4. R1 and R3, they are equal, they are fixed, so I can name them both the same. They can both be named R1, or indeed I can actually turn this equation around. First of all, R2 over R1 equals R4 over R3, or if I like, R2 equals R3 over R1 multiplied by R4. Now what I have here is that I have one sensor of unknown size. I have one variable resistor R4. What I can do is that I don't know R2, but I can now take the R4 and read the size of R4 in a different location. So as long as I know what size R4 is, I can say that it's the same as R2. As long as these two are the same, if these two are the same, R2 and R4 are equal when the bridge is balanced. So if I have a potentiometer like this one, what you see here is that you have a scale on the front side. So if I adjust this one to, say, for example, 3 blank, well, if I do that, then I know that the size of the potentiometer here is the same as my sensor. So if I adjust R4 to 3 kilo ohms, I know that's the size of R2, as long as these two are the same. So now I know the size of my unknown sensor resistor. That is a very manual way of finding an unknown resistance. As long as we have, well, it's called a balanced bridge, and it's very accurate because we can adjust AB to very close to 0 or with very high accuracy. So it's the most accurate way to find an unknown sensor at a difficult location. However, so as long as we have computers, I can take this equation and I can solve this with respect to the unknown resistance. And if I do that, I can put that into a calculator or a microcontroller and use that result from the voltage, measured voltage, to calculate the unknown. If you see here, this is the kind of equation that we have to put into our calculator. So now in this case it's named R2. Our unknown resistor R2 can be found if we know the fixed value of this one, fixed value, fixed value, fixed, 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 fixed. They are all fixed, apart from this one and this one, the one that we have to measure. And from that, we put this into a calculator and calculate the value of R2. So this is much more convenient to automate, and it's called an unbalanced bridge because the voltage across A and B terminals is not 0 volts.